Regular expressions are one of the most powerful tools available to a security automation specialist. They allow you to search, identify, extract, and manipulate text based on patterns rather than fixed strings. In cybersecurity, this capability is invaluable. Parsing log files, extracting IP addresses from command output, detecting suspicious patterns in HTTP responses, or validating user input are all tasks where regular expressions shine. In Python, the standard library provides the R module, which gives you full access to the regular expression engine. Before diving into syntax, it is important to understand what a regular expression actually is. A regular expression is a sequence of characters that defines a search pattern. This pattern can then be applied to a string of text to find matches, extract specific parts, or replace content. Unlike a simple string search, for example, checking if the word error appears in a line, a regular expression can describe complex and variable structures, such as a sequence of 4 groups of 1 to 3 digits separated by dots, which is the pattern for an IPv4 address. To use regular expressions in Python, you first need to import the R module at the top of your script. Import re. The most commonly used functions from the R module are re.searchPattern, string. Searches for the first location in the string where the pattern matches. Returns a match object if found, or none if not found. Re.matchPattern, string. Similar to search, but only checks for a match at the beginning of the string. Re.findAllPattern, string. Returns a list of all non-overlapping matches of the pattern in the string. Re.findIterPattern, string. Returns an iterator yielding match objects for all matches. Re.subPattern, replacement, string. Replaces all occurrences of the pattern in the string with the replacement text. Re.compilePattern. Compiles a regular expression pattern into a reusable pattern object, which is useful when the same pattern is applied many times. Understanding the basic building blocks of regular expression syntax is essential. Here are the fundamental elements. A literal character matches itself. For example, the pattern error matches the exact word error in a string. The dot matches any single character except a new line. So e.roar would match error, e_roar, error, and so on. The caret matches the beginning of a string. The pattern host matches any string that starts with host. The $, matches the end of a string. The pattern failed matches any string that ends with failed. The asterisk means 0 or more repetitions of the preceding element. So abc matches AC, ABC, 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 etc. The plus sign, plus, means 1 or more repetitions. So ab plus C matches ABC, ABC, but not AC. The question mark means 0 or 1 occurrence. So color matches both color and color. Curly braces, N, or N, M, specify exact repetition counts. So a 3 matches _A, and a 2,4 matches AA, _A, or AAAA. Square brackets define a character class, matching any one character inside. For example, AU matches any single vowel. 0 to 9 matches any digit. A Z matches any letter. The pipe symbol, vertical bar, acts as a logical OR between expressions. So cat vertical bar dog matches either cat or dog. Parentheses, create a capturing group. The content inside is treated as a unit and the match text can be extracted separately. The backslash is used to escape special characters or to introduce special sequences. Special sequences with the backslash are extremely common in security-related patterns. \D matches any digit, equivalent to 0 to 9. \D matches any non-digit character. \W matches any word character, letters, digits, and the underscore, equivalent to AZZ09 _. \W matches any non-word character. \S matches any whitespace character, space, tab, new line. \S matches any non-whitespace character. \B matches a word boundary, meaning the position between a word character and a non-word character. Let us now look at concrete examples relevant to cybersecurity and security automation. Example 1. Extracting IP addresses from ping output. In previous workshops, you ran the ping command using the subprocess library and saved its output. Now, suppose that output is stored in a string variable called output. A typical line of ping output on Linux looks like 64 bytes from 192.168.1.1. ICEMP_sec equals 1 TTL equals 64 time equals 0.456 milliseconds. To extract the IP address from this string, you can use the following pattern. Pattern equals are apostrophe backslash b backslash d1 comma 3 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 backslash b. Matches equals re.findall pattern, output.tt. This pattern uses backslash d1 comma 3 to match 1 to 3 digits, followed by a literal dot, escaped as backslash, because the unescaped dot means any character, repeated 4 times in the format of an IPv4 address. The backslash b anchors ensure we are matching complete IP-like tokens. The result of re.findall will be a list of all IP address strings found in the output. Example 2. Extracting open ports from an Nmap scan. When you run an Nmap scan and capture its output as text, you might get lines like 80/TCP open HTTP, 443/TCP open HTTPS, 22/TCP open SSH. To extract the port number and service name from each line, you can use pattern equals are backslash d plus slash TCP backslash s plus open backslash s plus backslash w plus. Matches equals re.findall pattern, nmap underscore output dot here, backslash d plus, captures the port number, slash TCP is a literal string, backslash s plus matches one or more whitespace characters, open is a literal word, and backslash w plus captures the service name. The result is a list of tuples, each containing the port number and service name, for example, 80, HTTP, 443, HTTPS, 22, SSH. This output can directly populate the port to service dictionary you built in previous workshops. Example 3. Detecting email addresses in text. In a phishing analysis or a web scraping context, you might want to extract email addresses from a block of text. A basic email pattern looks like pattern equals are az09._% plus backslash plus at az09. Backslash plus backs, a zazi2. Emails equals re.findall pattern, text.tis. This pattern matches common email formats by combining character classes for the local part, the @ symbol, the domain, and a top-level domain of at least 2 characters. Example 4. Using groups to extract specific parts of a match. Capturing groups allow you to isolate specific parts of a match. For instance, given the string failed password for admin from 10.0.0.5 port 3456 SSH2. You can extract the username and the IP address separately. Pattern equals our failed password for backslash w plus from backslash d. Match equals re.search pattern, log underscore line if match. Username equals match.group1. IP underscore address equals match.group2. Here, match.group0 returns the entire match string, match.group1 returns the first captured group, the username, and match.group2 returns the second captured group, the IP address. This kind of parsing is fundamental when analyzing authentication logs for brute force detection. Example 5. Using re.compile for repeated use. When you apply the same pattern to many lines, for example, iterating over thousands of lines in a log file, it is more efficient to compile the pattern once. IP underscore pattern equals re.compile r apostrophe backs, b1 comma 3, backslash dot backs, d1 comma 3, backslash dot backslash d1 comma 3, backslash d1 comma 3 backslash d, for line and log underscore lines. Matches equals IP underscore pattern dot findall line, if matches. Print matches. Compiling the pattern avoids reparsing the regular expression on every iteration, which improves performance for large datasets. An important concept to understand is the difference between greedy and non-greedy, lazy, matching. By default, quantifiers like plus and n, m are greedy. They match as much text as possible. For example, given the string b greater than bold/b and I greater than italic/I, the pattern less than greater than would match the entire string from the first less than to the last greater than because the greedily consumes as much as possible. To make it non-greedy, matching as little as possible, you add a question mark after the quantifier. Less than greater than would match b, then less than/b, then I, then less than/I as separate matches. In security contexts, this distinction matters when parsing HTML responses or protocol data. Another practical consideration is the use of flags. Flags modify the behavior of the regular expression engine. Re.ignore case, or re.I, makes the pattern case insensitive. For example, re.findall rarer, log underscore line, re.ignore case, will match error, 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 etc. Re.multiline, or re.m, makes and $match the start and end of each line rather than just the start and end of the entire string. This is very useful when processing multi-line log output. Re.total or re.s makes the dot match any character including new lines. A common mistake for beginners is forgetting to escape special characters. If you want to search for a literal dot, as in an IP address or a domain name, you must write \. In your pattern, if you write just, it will match any character. Similarly, if you want to match a literal parenthesis, a plus sign, or a caret, you must prefix them with a \. It is also best practice to use raw strings when writing regular expression patterns in Python. A raw string is prefixed with the letter R before the opening quote, like r'\d+. This tells Python not to interpret \ sequences as Python escape sequences, such as \n for new line or \t for tab, which prevents conflicts with the regular expression engine's own use of backslashes. In the context of security automation, regular expressions are used constantly to parse the output of tools like Nmap, Nixto, or custom scripts, to extract credentials or tokens from captured traffic, to detect malicious patterns in input validation, to search through log files for indicators of compromise, and to automate the generation of vulnerability reports by extracting structured data from unstructured text. The combination of the subprocess library, which you use to run system commands, and regular expressions, to parse their output, forms the backbone of many practical Python security automation scripts. To summarize the key points of this chapter, regular expressions define text patterns that can be applied to strings to find, extract, or replace content. The Python module provides functions such as re.search, re.match, re.findall, re.findEditor, re.sub, and re.compile. The core syntax elements include literal characters, the dot, anchors, caret and dollar, quantifiers, plus, n, m, character classes, alternation, vertical bar, capturing groups, and special sequences, \d, \w, \s, \b, etc. Capturing groups allow you to extract specific parts of a match using match.group1, match.group2, etc. Always use raw strings, R, when writing patterns to avoid conflicts with Python escape sequences. Compile patterns with re.compile when reusing them in loops for better performance. Use flags like re.ignore case and re.multiline to adapt matching behavior to your needs. In cybersecurity, regular expressions are essential for parsing tool output, analyzing logs, extracting indicators of compromise, and automating report generation.